this chapter sets the stage for the whole course, so it's running through everything from energy balance to atmosphere, ocean circulation, paleoclimate observations, and now carbon cycle. So let's systematically go through them. Obviously, carbon cycle is incredibly important for understanding climate variability and climate change, because CO2 has always been part of climate change at glacial deglacial scales that we talked about, with increase during deglacial times and sequestering of CO2 during glacial times. And now human beings are perturbing the carbon cycle and also the nitrogen cycle heavily because of fossil fuel burning. But we need to understand how the carbon cycle actually works. So this is the latest one from last year from a paper by Friedlingstein et al., which I didn't put here unfortunately, but you can look it up. So the pools and fluxes are shown here, like volcanic flux in gigatons carbon per year, and these are gas reserves, oil reserves, and coal reserves. So you look at stocks in reservoirs and you look at fluxes as exchanges between them, mostly between fossil fuel burning, atmosphere, ocean, vegetation, and so on. So this is for the period of 2009 to 2018. This gets updated every year. They do an incredibly good job. So this is showing fossil CO2 effective flux, land use uptake, so going down. This is the land use change, so deforestation, urbanization, forest degradation, and other things. Stocks in vegetation, soils, permafrost, and surface sediments, deep ocean, dissolved organic carbon, and so on. What the atmosphere keeps in terms of the annual rate of increase, and its reservoir stock. So it's concentration in ppm by volume, or gigaton carbon as the amount that is there in the whole atmosphere, right? So there is uptake of the ocean. The problem in figuring out these numbers is that you can see photosynthesis takes up about 120 and respires back about 120. So there are two huge numbers with a small flux in or out of the system. So it is that system uptake or emission that's very critical for accounting the carbon cycle. That's what is really difficult. So even after they do all this careful calculation, they tell you that there is a budget imbalance of plus 0.4 gigaton carbon. Sometimes it is referred to as the missing sink and so on. But essentially, there are some reservoirs that are taking up CO2 that we don't know where it is. Okay, so people work very hard on figuring out. So it's a scientific uncertainty and not any kind of mistake or a false claim. Okay, so you can see that the ocean holds a massive amount of inorganic carbon, 38,000 gigatons. Marine biota hold about 3. Ocean carbon itself holds about 700. And there are also sources in the sediments that are very large. And the fluxes are important because we are increasing the carbon in the atmosphere and we need to know where it's going. So if you look at CO2 flux in gigaton CO2 per year, okay, so fluxes are always per unit area and time. Here they are averaged over the globe. So fossil fuel and cement, we know very well how much they emit because they are commercial products and very closely tracked, and we know how much they emit. This is a few years old, but nonetheless, land use change, as we mentioned, is emitting some carbon now because of vegetation perturbation. Especially tropical forests are losing carbon, which is bad news. In fact, with warming, respiration also increases, so we have to be careful. And there is the sink in the land, which can be estimated based on various measurements. There is what remains in the atmosphere, and that's what is going into the ocean. You can see that the ocean and land are trying to take up more over time, and the atmosphere is accumulating more as well. But the land has a lot of perturbations. It's not as deep and steady reservoir as the ocean. Okay, so these are critical things to watch out for, and this has to be placed in the context of what we are doing in terms of emissions, right? Just fossil fuel burning as registered in Mauna Loa is showing a steady increase of plus 0.49, as this is indicating in terms of a flux. Okay, so that's not small. So we are increasing this more and more, and despite the 25 years of negotiations, there is no indication that greenhouse gases are decreasing yet. So to meet some of the targets, we have to start reducing them now. So if you remove the trend and look at the time rate of change of CO2 fluxes, you will see that there is year-to-year variability. So this is the CO2 growth rate in the atmosphere in petagram carbon per year. So if it is negative, that means there is carbon being taken up, and if it's positive, that means carbon is being emitted. So this is showing relations between temperature and precipitation and CO2 fluxes. Going back to the Köppen vegetation classification, where he assumed that there is a close relation between precipitation and vegetation, this does show that there is a high correlation, except in years where there is volcanic eruption like Pinatubo. It can get thrown off. Waiting for a second here again for my friendly chopper to pass. So things like volcanic eruptions and El Niños change things. We will see in a minute. So Amazon drought, for example, warmer temperatures and carbon emissions. There is several droughts here, 05 and 10. There are several volcanoes. So point is, the CO2 in the atmosphere varies year to year, and it can be related to natural variabilities like droughts and El Niños and volcanic eruptions. But the question is how global warming and precipitation changes are affecting these sources and sinks. Okay, ocean, which is a huge reservoir, as we just saw, has flux out of the ocean and flux into the ocean. So where it is red here, ocean is bringing up high CO2 water close to the surface, decreasing the pressure difference between the ocean and the atmosphere, or the ocean surface is getting so high in partial pressure of CO2 that CO2 escapes into the atmosphere. Just like a Coke can, if you keep it cold and sealed, because high pressure and cold temperatures keep the CO2 dissolved in water. But if you open the Coke can, immediately you release the pressure and CO2 is going to start escaping. Something similar happens here as well. There are alkalinity of the ocean, which complicates things a little. There is a buffering ability in the ocean, which complicates things a little. But you can see that there are places where ocean takes up CO2, especially the Southern Ocean and these storm tracks and the Gulf Stream and the Kuroshio regions and so on. And the upwelling regions here and here outgas CO2 from the ocean, and these are the interannual variability of that. So year to year, because of El Nino and so on, and because of the storm tracks, etc., there are variabilities in the flux. What we need to watch carefully is whether the amount of ocean uptake of CO2 is decreasing, or is the ocean getting saturated with anthropogenic carbon. This is critical to watch out for. So data has to be collected. Remember the Argo biogeochemical float we talked about, which stays at about 1,000 or 2,000 meters and comes up every few days to beam data. they are being used to collect CO2 type data to see what exactly is happening to the anthropogenic invasion of CO2 into the ocean, and where ocean is beginning to lose its ability to take up CO2 because of global warming, because warm waters solubility goes down, right? So we have to be careful.